Thanks a lot again to come.
All right, thanks very much for the introduction and the invitation. So I will talk about double copy, double field theory, and homotopy algebras. And so I will explain all those terms, of course. So this is based on joint work with my former student, Felipe Diaz, and Jan Plevka initially. And then there are a couple of follow-up projects together with two postdocs, Roberto Bonezzi and Christoph Chiafrino, which may or may not be in the audience. And so if you have much more technical question than I can answer, maybe they can help. So let me start with an overview of motivation and strategy. So what I want to talk about, or what I want to explain and understand, is called double copy. So you probably heard about it. It's a structure that people discovered in scattering amplitudes. And that is often summarized under the slogan, gravity is Young-Mills squared. So the scattering amplitudes of gravity have this interesting property that is not obvious at all at first, that you can reconstruct them from Young-Mills theory. So there's a certain procedure to take a Young-Mills scattering amplitude, to strip off color factors, to rewrite the form, the amplitude in a suitable form, and then you can double copy them, take two copies of that object and build a gravity scattering amplitude. So that's something that, in fact, has an origin in string theory, where it's known under the name KLT relations, and was brought to the field theory form by Byrne, Carrasco, and Johansson in 2008. So there the relationship is about proper Young-Mills theory and not open string field theory. And a version of gravity, sometimes called n=0 supergravity, which is not really supergravity, it's normal gravity, Einstein-Hilbert gravity, coupled to an antisymmetric tensor, the so-called B field, and a scalar field, the dilaton. And the question is, why is this true? Why should this happen? If you just look at the textbook definitions of Einstein-Hilbert gravity, Young-Mills theory, they have nothing in common, very little. The Lagrangian for gravity is, if you expand around the background, is non-polynomial. You have infinitely many couplings, you have infinitely many vertices. In comparison, Young-Mills theory is very simple, just has cubic and quartic vertices, and then it stops. And of course, physically, we know they're also very different. So it's very intriguing that there should be this deep relation between gravity scattering amplitudes and Young-Mills scattering amplitudes. So one question is, can you prove this? And perhaps, can you push this beyond scattering amplitudes? So can you go off shell? Can you maybe understand this in a gauge-independent manner? So when you compute scattering amplitudes, of course, we always go on shell and fix the gauge and so on. So is there maybe a off-shell gauge invariant, and most importantly, local first principle derivation of this relation? And so today, I will introduce a framework or a program where such a derivation may happen, and that uses the framework of homotopy algebras. So homotopy algebras in physics, at least, were discovered in string field theory. So that's why this is a nice venue to talk about this. But here we'll strictly apply to standard field theories like Young-Mills theory, but we'll see many structures that, in fact, you're familiar with from string field theory. So the program here is that we take Young-Mills theory and we view it as a certain so-called homotopy algebra, an L-infinity algebra. And I will explain what all this means. I will give a self-contained introduction. And so we'll realize this L-infinity algebra as the tensor product of a Lie algebra, a simple Lie algebra G, frac G, and another kind of homotopy algebra, which I denote here calligraphic K, which you therefore can think of as the kinematics of the theory. So if you take out color, what you're left with, you can call kinematics. And that itself is a homotopy algebra of a different kind, as I will explain. And most importantly, there's also some hidden new Lie algebra type structure, which is not exactly a Lie algebra. It's also not even a homotopy Lie algebra. It's something, there's a version of a BV or Bartalin-Wilkowicki algebras with two decorations here, which I will explain in due course. So now the idea is to get gravity out of this in the form of what's called double field theory. So double field theory is a formulation of gravity or n equals 0 supergravity that is particularly convenient for this purpose because it has this kind of left-right factorization built in that you get by taking the tensor product of two copies of this kinematic algebra. So the color factors are gone. Now just the kinematics. I introduce a second copy. So instead of tensoring with the Lie algebra or color Lie algebra G, I tensor with the second copy of the same kinematic algebra, which also has this Lie type structure. And on a suitable subspace, at least I obtain an L-infinity algebra. And an L-infinity algebra is something that encodes a field theory, and this is double field theory. At least we prove this to quartic order. The construction works to quartic order so far. And finally, I will not have much time probably to go into detail, but I will mention something called weakly constrained double field theory. So when I say double field theory is a reformulation of n equals 0 supergravity, that's true for something called strongly constrained, but there's also weakly constrained version, which is truly stringy in the sense that you have momentum and genuine winding modes on toroidal backgrounds. So construction of this theory explicitly to quartic order was an open problem until we realized that in this framework, at least for purely toroidal backgrounds, it can be solved to quartic order before it was known to cubic order. So that's the general motivation, double copy, proving it from first principle using homotopy algebras. And here's the outline. So I was asked to give a half an hour self-contained introduction for non-experts. So everything here will be self-contained, I hope. And I'm not sure if I will use all the 90 minutes, but I will use the first, I don't know, 15, 20 minutes or so to give a general introduction via the toy model of Schoen-Simons theory. So there we actually have not genuine homotopy algebras, but so-called strict versions. But apart from that, all the essential ingredients of the stuff I will need are already present. So you see in a familiar setting what will then generalize to Young-Mills theory. And then the second part, I will introduce the homotopy algebra formulation of Young-Mills theory or the L-infinity algebra. So first the general framework, what is an L-infinity algebra, then how it encodes Young-Mills theory. And then the third part, we can explain how this homotopy algebra framework allows us to give a meaning to this notion of color decomposition or stripping of color factors, which in homotopy algebra means that there's really a kinematic homotopy algebra, which is a different kind than an L-infinity algebra. And then in the final and fourth part, I will explain this construction of what's called double field theory, which is a gravity theory, as the double copy of Young-Mills theory. And then I have a brief outlook. So please feel free to interrupt me at any time. So let me start with the general introduction using 3D Schoen-Simons theory as a reminder. Okay, so let's start with something simple. Let's start with differential forms, something we all know. So when we have differential forms, let's assume we're in 3 dimensions because we ultimately want to do Schoen-Simons theory. That means that we have the space of differential forms, which is called the de Rham complex. So we have spaces here of 0 forms, 1 forms, 2 forms, and 3 forms, omega p, where omega p is the space of p forms. And of course, it stops at 3 forms. So we draw this as this so-called chain complex. So we have a sequence of vector spaces. And we have, of course, the de Rham differential that increases the form degree and hence maps between these spaces. And then, as I said, since we're in 3 dimensions, it stops here. So indicate this by a 0. And this is a chain complex because the composition of 2 gives 0. D squared is 0. Then I write a generic P form in this form here. So I'm allowing myself a notation that turns out to be convenient in a second, where I write the basis elements that we conventionally write as dx mu as theta mu's. So you can think of the theta mu's as anti-commuting variables, because if you have theta mu, theta nu, and you change the order, you get a sign. So in that sense, they're odd variables, and you can think of them as degree +1 variables. But other than that, it's just the ordinary expansion of a differential form here. So that's the vector space. It's this complex. And then we, of course, have an algebraic structure in this vector space, which is just the wedge product. So given two differential forms, I can take the wedge product. And if I think of a differential form as written here as a function of theta, this wedge product, in fact, is just the ordinary product of functions. So if I multiply two such functions, I get two sets of theta, so the degrees add up. If you write it out in components, of course, you realize that's just the standard wedge product. So in particular, it's symmetric or anti-symmetric, depending on the degrees of the forms. So this is what we call graded commutative product. So it's not strictly commutative, it's graded commutative in the sense you may pick up a sign depending on the degrees of the inputs. And then we have the Durham differential D, which in this form is just theta mu, the derivative with respect to x. And here I've given two new fancy names to these maps. The differential I also call M1, and the product I call M2. So D squared equal M1 squared is 0. Now you will wonder, why do I give a new name to something that has already a name? So large part in this activity is that you give new names to familiar objects. So what's the point of that? Well, the point of that is that the general structure may re-emerge in a different context where these maps are just something completely different. Particularly in a moment, we'll see an example where this is not the first order differential operator in general, but something else. So it's very useful to have a sort of give general names to these objects, identify the general structure, and then you can potentially recognize it somewhere else. So that's my excuse for calling it M1 and M2. So M1 squares to 0. So it's the same as the Durham differential. And it satisfies these two relations. So M1 acting on M2, the product, acts via the Leibniz rule. So if you have M1 from the outside, you can move it inside according to the Leibniz rule, where you pick up a sign here, potentially. And M2 is also associative. We know, of course, the wedge product of forms is associative and expressed in the M2. This is just the statement here that if you move the M2 over in this fashion, it's the same thing. So this is an example of what's called a strict C-infinity algebra. It's, of course, just a graded commutative associative algebra. In fact, it's a differential graded commutative associative algebra. And this will be generalized in a moment to something called C-infinity. C refers to commutative. And so this is a strict example. Strict C-infinity algebra, which, for those of you who know the term, it's the commutative case or special case of an A-infinity algebra. Okay. So that was a reminder of differential forms. So we want to get to Schoen-Simons theory. There's, of course, something important missing, which is the Lie group, the gauge group, the Lie algebra of the gauge group. So I will call this frac G here. And this is what we call Kähler factors. And if I bring in the Kähler factors, we'll see a different kind of algebraic structure emerge, which is a Lie algebra, or in fact, a differential graded Lie algebra. So how does that work? So we tensor the total space we had before with the Lie algebra G. So I have this chain of vector spaces here, where each space is the space of forms tensored with the Lie algebra G. And that just means in practice that the differential forms become G-valued. So if you expand the one form, for instance, I have now this expansion here. We have two indices, the one form index mu and the new color index A that contracts the generators. And sometimes I write it like this, suppressing the one form character. So then A summed with TA is just meant with the understanding that AA is a differential form, so one form in this case. So what happens to the graded commutative and associative product we had before? Well, now it actually gives rise to a Lie bracket or a graded Lie bracket in the following sense. So if I have this expansion, let's say, of two differential forms, I can take the components A1B, A2C. They are still objects in the original vector space because the color indices here sitting on the A's are just labels, if you wish. I can plug this into M2, means just the wedge product of forms. Then, of course, I have two free color indices, which I don't have on the left-hand side. So I can use the structure constants to contract them, FBCA, and then I have a free A index that I contract with the TA. So in that sense, I produce now an output that lives in the total space of G-value differential forms. And now you can check that this has the properties of a graded anti-symmetric or symmetric, depending on the convention, Lie bracket, because before the M2 was commutative, graded commutative, but you pick up an extra sign because the entries here are now contracted with the structure constants, which of course anti-symmetric. So it has the right symmetry properties to be a Lie bracket. And in fact, it also satisfies the graded Jacobi identity. So while before we had a two-term associativity relation here, if you work it out in this combination, you see using the Jacobi identity of the structure constants, that this new bracket also satisfies the Jacobi identity with the appropriate signs, which means that we have a graded Jacobi identity. And so the structure that emerges is called a differential graded DG Lie algebra, which is the case, which is strict L infinity algebra. So L stands for Lie. We'll relax these axioms in a moment. That defines the L infinity algebra. And so this is the strict case where there are no higher brackets. So that's the structure I have. I have a differential that squares to 0, D, and I have a bracket acting on G-valued forms such that this differential squares to 0. It still acts by the Leibniz rule on the bracket, and the bracket satisfies now a graded Jacobi identity. So given such a differential graded Lie algebra, I can write this action, which you'll recognize as the familiar Schoen-Simons action. Once I define also an inner product, which for forms, of course, is just the wedge integral, wedge product of the three form, where the color indices are contracted with some Cartan killing type metric. So given also some inner product, you could call this a cyclic differential graded Lie algebra, and that's what you need to define in action, or without it, you can only define the equations of motion. So you have the familiar equations of motion of Schoen-Simons theory, you have the familiar gauge transformations, and in order to check anything you like gauge invariance of the action, you need precisely the axioms of a differential graded Lie algebra. So that's all you need. And in this particular construction here of Schoen-Simons theory, I sort of immediately built it by explicitly having two ingredients: an algebra of differential forms, a color Lie algebra, and just tensoring them together to get this differential graded Lie algebra. And so if I think in reverse, stripping of color is just going back to the pure differential forms. So in that sense, in the case of Schoen-Simons theory, the kinematic algebra is just the algebra of differential forms in 3 dimensions, which is an example of a strict C infinity algebra. Okay, any questions so far?
Olaf, just a small question. So in the previous slide, when you write M2, so it's defined as a contraction of omega and eta. Omega and eta can be any P form.
Yeah.
Okay. So it's not just one form here.
It's any P form. Okay. And of course, on the entire the RAM complex, you need it. You want it between arbitrary P forms. that was here. And this formula here works also for arbitrary forms. There's a sign which depends on the inputs, the form degrees of the inputs. This here was just an example.
Okay, great. Thanks.
Okay. So now we've just revisited Chern-Simons theory in 3 dimensions, the familiar construction. All you need is the differential forms, and you have to pick a Lie algebra if you want an actual Lie algebra with an inner product. And then you build, that's normally not how it's presented, but effectively you're building a new algebraic structure, the differential graded Lie algebra that I defined here. And that's what you need to check the consistency of the action. Okay, now it turns out there's some extra structure which uses a little bit more than what's given to you initially, but that's also what we'll see later in Yang-Mills theory, and which is what you really need to do the double copy thing. And this extra structure is a version of what's called the Batalin-Wilkowiski algebra. Okay, so why is there some extra structure? What I mean by this is that even though basic Chern-Simons theory is beautifully topological, you don't need a metric or anything to write it. It's just there on any 3 manifold, as long as the Lie algebra has an invariant bilinear form. But in order to do any sort of real computations, like quantum computations or Witten's famous the treatment of the Jones polynomial and knot theory, etc., you have to fix a gauge, for instance, and in order to do that, you have to pick a metric. So this I call you spurious metric, because you have to pick one, and then nothing is supposed to depend on it. So it doesn't really matter which one you pick. And at the end, things will be independent or should be independent of this initial choice, but you have to pick one. So this gives you now an extra structure, which turns out to be important for the double copy. So let's say we have a metric G mu nu. Let's think just flat Euclidean metric, for instance. What does it mean? That means you have now a Hodge duality operation between differential forms, which you don't have if you don't have a metric. And you have an adjoint of the de Rham differential D dagger. And that one is defined here. It's just star D star with some sign that is signature dependent. So you take the star of a form, means you send it the P form to a 3 minus P form in 3 dimensions. You act with D, and then you star it back. So then it's an operation that keeps, well, it's an operation that lowers the form degree, it turns out. So it's a differential that goes in the opposite direction. Well, the de Rham, if it goes this way, the D dagger goes the other way. So in that sense, they have opposite degrees. And following my previous apology for giving a second name to everything, here I also want to call it B, because B will reappear as a completely different object later, but satisfying the same kind of relation. So that's why I'm giving it 2 names here already. And what is useful of this thinking of the basis elements of differential forms as odd variables theta is that you can give an expression here as a second order differential operator. So what this D dagger really does is it lowers the form degree by taking away 1 theta, then taking the derivatives with x mu, using the metric to construct the index. So it's like taking a divergence of a form. So it lowers the form degree and goes in the opposite direction. But it also squares to 0. As you know, D dagger squared is 0, and which is manifest from this expression because the thetas are anti-commuting while the x's are commuting. So if you square this, you get 0. More importantly, or interestingly, the B is hence a kind of a second differential, squares to 0. It has the opposite degree to the D, the de Rham differential, which I also called M1. So it makes sense to take the anti-commutator, because then it's a degree 0 operation. Degree 0 operation here really means that acting on a form, the P form, it gives you back a P form. So it doesn't have an intrinsic degree that adds a form degree. Well, what's the anti-commutator? It's M1 is D, B is dagger, d dagger. So you have d dagger plus d dagger d, and you know that's one way to define the D'Alembert or Laplace operator. So that's just the second order Laplace or D'Alembert operator that you can define given the metric g mu nu. Okay, so we said that B is the second differential. So now you can ask, well, if it's differential, does it act via the Leibniz rule on the product that we have, which I called M2 before? And it's just the wedge product of forms. And the answer is no, it does not act via the Leibniz rule. Rather, its failure to do so is an interesting structure in itself. So this we typically denote in this notation here. So I put in the quotation marks because this is like the commutator of B with M2, which you can give a precise meaning, but I don't have the time for that. What I mean by this is simply B acting outside M2. So M2 is taking the product, you act with the B outside, and then you take minus the B's acting inside. So this is the combination of terms that would be zero if there was a Leibniz rule for B and M2, but it's not actually zero. So let's give it a name. We call it B2 because it has two inputs exactly like the M2. And now it turns out that this is actually a graded Lie bracket. And using this formulation with the thetas, etc., you can quickly see why it's not zero and what it is. In fact, it's not zero because this is a second order differential operator. It's a second derivative. So if you take the second derivative of a product of two functions, you get these mixed terms, which you see here. So it's a d theta mu, dx nu, contracted with eta mu nu. So that's the kind of term that survives and has this Poisson bracket type structure. And if you work out what this is in differential form, for differential forms, this is actually related or equivalent to something called the Schouten-Nijenhuis bracket, which is a bracket defined for polyvector fields, not for differential forms. But we assumed already that we have a metric. So if I have a metric, I can identify differential forms with objects where all indices have been raised using the metric, and those are called polyvectors. And they have an interesting Lie algebra structure, which is called Schouten-Nijenhuis. What is this bracket? If you've never seen it, well, you know what a vector field is. A vector field is a first order differential operator. So you can take the commutator of two vector fields, and this is just the Lie algebra of diffeomorphisms. Right? So diffeomorphisms infinitesimal generated by vector fields. So it's a diff algebra. And this can be extended to polyvector fields of arbitrary rank. So the extension is the Schouten-Nijenhuis bracket. But it's, of course, amusing that at the level of vector fields, this construction contains the standard diffeomorphism algebra. Okay, so what is this weird thing? You have a product M2, it's associative. You have a differential B, but it does not act via the Leibniz rule. In fact, you can check out that B acting on B2 acts by the Leibniz rule. On the bracket B2, which one you think of as a Lie bracket, acts by the Leibniz rule. So that means that B and B2 together form a differential graded Lie algebra as just defined. And if we ask, well, what is the larger structure if I also remember the M2, the associative product, the commutative associative product, it's called a Batalin-Wilkowicki, or for short BV algebra. So if I have this differential graded Lie structure with a product on which the differential X acting as second order in the sense described here, which can also be expressed algebraically, then we call this a BV algebra, and then you get various consistency conditions. So you have the B2, a Lie type bracket, you have the M2, an associative product, and they satisfy compatibility conditions, which are analogous to those of Poisson algebra. So if you have a Poisson bracket on some space of functions, like functions on phase space and mechanics, then you also have the product of functions, and then you have compatibility relations between the brackets and the product, and that's also part of this BV algebra. Okay, but here we should remember that there's even more structure, because there's also the M1, the original differential, the D. So if I have two differentials of opposite degrees, and two products of brackets, an associative product M2 and a Lie bracket B2 that satisfy suitable relations, this would be called by mathematicians a differential graded BV algebra, because it's a BV algebra, it's an extra differential. But it's not actually quite that because of this relation up here. So if M1 and B, the two differentials, which are of opposite degree, if they would anti-commute, then everything would be nice, but they don't anti-commute. From this basic relation, we see they anti-commute to box, the wave operator. So this is not a DGBV algebra because it has these what we call box failures. So relations you would impose fail due to box being a second order operator. And this, hence we call here, I call here BV, box algebra. So that's a funny name, but that's just the structure you have. And the interesting thing is that all these algebras we encountered here will reappear in basically the same form, except everything is up to homotopy. Everything will get a little infinity subindex. And then these algebras are also there in Young-Mills theory. Okay, so that was basically everything I wanted to say as a review of Chern-Simons. Are there any questions so far? Maybe just a live sign that people are still around.
We're here.
Olaf, I have a question.
Yes.
So this, okay.
Hi.
Hi, how are you doing?
Good.
So this D dagger is the B ghost in the context of open string field theory, right?
Yes, that's how.
And D is the PRST operator. So do you have any like understanding what is the star in the case of open string field theory? Like, is there like operator, like hot stars?
Yes, no, I don't. Yeah, it's not obvious that this particular realization is of this character to me, but I have not thought about it. Yes, I don't know.
Okay.
Okay. More questions?
Yeah, I have a question. So can you give an explicit example, like how can you use this B idea to really do computations in physics? Because for me, it's like abstract, too abstract. You define something and you said it is useful for quantum computations, but which quantum computation? Can you show some examples?
For instance, if you want to define the propagator, it's basically B over box. So in Chern-Simons theory, you know, the propagator is something like D dagger over delta or box, the Laplace operator, the D'Alembert operator. And so in order to write that, of course, we need this extra structure, which normally you just say you pick a metric and then you write it. But here, more abstractly, in fact, the B is the object that allows you to write the propagator. That's one example. The other one is, which probably should come first, is B is the object that allows you to write the gauge fixing condition. So if you have a field psi and you said B psi is 0, this is a good gauge fixing condition. But we'll see B in another context, a different kind of B later. It's very abstract, I agree, but it's useful to go to this next level of abstraction because then this will allow us to recognize the same structures in a very different context, which is Young-Mills theory. So Young-Mills theory, the way we write it concretely in physics normally, and you compare it with Chern-Simons theories, they have nothing in common. It's a very, very different theory, except that you have, of course, Young-Mills style gauge fields, but other than that, they look very different. But if you accept this slightly higher level of abstraction, or not slightly, but quite a bit more abstract, I agree, you can then recognize all kinds of similarities.
Okay, thank you. Another question, in BRST language, this B ghost is like what? The anti-ghost in BRST, like action goes to action plus Q something. Is this something, the B, or no, it's something else? Like in usual BRST, don't go to BV, you deform the action by Q exacts, and then you break gauge transformations by Q exact deformations.
Maybe one
Is
of the
this the B the anti-ghost?
yeah, I think so, but maybe someone in the audience can confirm that. Probably someone knows that better than me.
Yeah, so I'm not Giuseppe, I'm Roberto Bonetti. So yeah, so the B, we call it B because it can be interpreted as the B ghost of an underlying first quantized realization of Chern-Simons. And the gauge fixing in this case would correspond to what you normally have as Siegel's gauge in string field theory.
But was that, does that answer the question?
Yeah, more or less. Thank you. Thank you.
Okay, thanks.
I was a little confused about the emphasis on the letter B.
Yes, it's just that that's the physicists get very attached to letters, particularly. So if you once name something with a certain letter, if you use the same letter later, you can recognize it's related. But it's just the second differential, and I just call it B here because a similar map later we'll also call B, which concretely looks very different, but the general algebraic structures are similar.
That's fine. I didn't quite understand Imran's question.
Sorry, my question.
Yes.
I just want to understand if you can translate this B in BRST approach. Like physicists has a way of dealing with gauge symmetries and Chern-Simons using BRST symmetry, which is essentially this M1, but you usually deform the action by Q exact.
Yes.
And this Q exact is Q of something. This something is like an anti-ghost. So I'm trying to understand if the B is this something or not.
There is certainly a place, I think it gets added to what he has here so far, add ghosts and anti-ghosts.
Well, anyway, maybe we can come back to it. This is sort of tangential to the purposes here. I mean, what will come back is this anti-commutation relation between M1 and B, that they don't anti-commute. And therefore you have this deformed kind of BV structure. Okay. So let me then maybe come to the second part. So now we come to the real theory we care about. I don't really care about Chern-Simons theory. Well, I do, but not in this context. I care about Yang-Mills theory and gravity. And there you, as I emphasize, you have the same kind of structure, except everything holds up to homotopy. So you obtain homotopy algebras. Let's start with the sort of general kind of dictionary between L-infinity algebras and what I call here perturbative field theory. By perturbative field theory, I just mean that you have something like an action, or at least equations of motion, where you have an expansion in powers of fields. So here you have a field A, you have a term quadratic in A, you have a term cubic in A, you have a term 4A, so it's quartic in A, etc. And I've written the action in terms of certain maps. B1 with one input, B2 with two inputs, B3 with three inputs, etc. And this is exactly analogous to the Chern-Simons action, the one here. Except now I've given new names to the differential. So B1 is a differential. B2 is something like a Lie bracket, except it's not exactly a Lie bracket because I have these higher maps. So this is what defines an L-infinity algebra. I have an integer graded vector space. So as we had the Ram complex of differential forms, in general, I may have an integer graded vector space, but this could range over the whole integers. Usually it stops somewhere, but it's not necessary that it does. I'm sorry. And then you put a structure on this space, which is encoded in these graded symmetric maps, B1, B2, B3. So in the strict case, we had only B1 and B2, which was the differential and the graded Lie bracket. But now we have potentially an infinite number of higher maps. And the conventions I'm using, they have all the same degree, +1. And that just means that the degree of the output is the sum of the degrees of the input +1. Okay, and now I have relations between them, which are the generalized Jacobi identities. So B1 is still a differential that squares to 0. B1 squared is 0. B1 is still a differential that acts via the Leibniz rule on B2. So the B2 is the kind of generalized version of a Lie bracket, and you have this relation here. And then the real change, the first change happened here, if you look at the Jacobi identity. So the standard Jacobi identity would be this combination of 3 terms of nested B2s with some appropriate signs because we're in the graded context. And in the strict case, this combination of 3 terms, which we sometimes call the Jacobi, that would just be 0. But in this context, this can be corrected by terms involving this 3 bracket and the differential. So the second line here is kind of the kind of terms that would be 0 if B1 acts as a differential on B3, but here it's not 0, but compensates for the failure of the Jacobi identity to hold. And then there's an infinite tower of higher relations, potentially infinite tower of higher relations. They can be written in a closed form, and there's in fact a very neat closed form characterizations in terms of co-algebras and co-derivations that Jim could tell us all about, but I won't really need it. You can look it up if you care about. Got it? I just want to use that there's potentially this algebra. Well, there's such an algebra, and it codes fields theory in this fashion. So first by defining the action, but now also defining things like gauge transformations and field equations, etc. Okay, so let's see how it works in an example, the example we care about, which is Young-Mills theory. So I use a formulation of Young-Mills theory that is written here, which in fact is kind of suggested by string field theory, where you have an extra auxiliary scalar phi. So here I've written out the quadratic terms with 2 fields. Here the cubic terms, here the quartic terms. The bracket here now is just the color Lie algebra Lie bracket. And you see here phi is an auxiliary field. You can integrate it out. On shell is equal to the divergence of A. If you plug it back in the action, you can quickly check that it's the familiar kinetic term, free kinetic term of Young-Mills theory. Now it looks a little silly to introduce this phi, but actually will turn out to be very convenient in a second. And here the fields, of course, are Lie algebra values. Now the L-infinity algebra here is defined again on a 4-term chain complex. So this has 4 spaces that are what I meant by 4-term. And in that sense, it's exactly analogous to Schoen-Simons theory in 3 dimensions, where we also had 4 spaces. And although the spaces are different, their interpretation is basically the same. Meaning that we have a space here. The degrees are a little shifted compared to the RAM complex. That's again a matter of convention and is here for convenience. But we have this low space here, which you can think of as the space where the gauge parameters live. So we have a gauge symmetry, hence gauge parameters, and that's the space where it lives. Then the next space is the field space, which normally is just the Young-Mills gauge fields A mu, but here I call it calligraphic A because there's the second component, the auxiliary scalar phi. Then you have another space, which you can think of as the space of equations of motion, or in the more standard PV context, you would call this anti-fields. It's just, you need a space where the variation of the action or the equations of motion live. And then there's one more space, which in Schoen-Simons was the space of 3 forms, which you can think of as encoding Noether identities or Bianchi identities. So what's exactly the dictionary? The dictionary is the following. If you look at the linearized part of the gauge transformations and the equations of motion, they are just determined by the differential. So the infinitesimal gauge transformation on A is just B1 lambda. And the free part, the linear part of the equations of motion is B1A equals 0. And so you can check that they look like this. So this is the gauge transformation of A mu. A mu just goes to d mu lambda. The gauge transformation of phi, in fact, is just box lambda. You can check this by going on shell. And the linearized part of the equations of motion is here the equation of motion for A mu. It's box A mu minus d mu phi. The equation of motion is for phi is d dot A minus phi. So if you set it equal to 0, it tells you phi is equal to d dot A, which is the divergence of A. So you see here why you could probably first hint why the introduction of the phi is useful. It allows us to single out the box in a gauge invariant manner. So I didn't have to fix any gauge. I have terms with a box and then sort of corrections involving the phi. And this will turn out to be useful in a second. Now, just to complete the dictionary, the nonlinear Yang-Mills equations take this form here. It's generalized, known as a generalized Mara-Katan equation, if you just define the B2 and the B3 properly. So the B2 looks like this, has one derivative in it, it's this set of terms. The bracket is again the standard color Lie algebra bracket. And then you have a B3, which is just this nesting of two Lie algebra brackets, and then a bunch more terms for symmetry. So that's the equation of motion. You also have the gauge transformations, which use the B1 of lambda, as I just reviewed, and a 2 bracket with two different kinds of inputs now, a lambda and a, so a gauge parameter and a field. And this is an independent object that has to be defined properly. It's done here. And then there also B2s with two gauge parameters, for instance, which encodes the gauge algebra, etc., etc. So you can make a list. And if you check the classical or perturbative consistency of Yang-Mills theory, let's say checking gauge invariance of the action or gauge covariance of the equations of motion, or that the gauge transformations close. So kind of a standard list of exercises that you would do in a QFT class when you introduce Yang-Mills theory, re-expressed in terms of the BNs, these maps. These are just the generalized Jacobi identities. So these kind of relations here that define an L-infinity algebra is exactly what you need to check the consistency of a classical field theory. So in that sense, L-infinity algebras are sort of the abstract essence of a perturbative classical field theory. So consistency is precisely encoded in these L-infinity relations. Okay, any questions on that? There's something in the chat I see. Is that comfort food? Very good. So that's just the introduction to L-infinity algebras and illustrated with Yang-Mills theory. Now the third part will be to extract from this, to take out the color factors now, because that was the initial motivation, and to define what I call here the kinematic homotopy algebra. So kinematics means everything that's left when you sort of ignore the color factors. And in the normal field theory way of thinking, it would be very confusing what this could possibly mean. There's no Lagrangian you can write for Yang-Mills gauge fields where you skip the color factors. So that doesn't really make sense. But at the level of algebras, homotopy algebras, it makes perfect sense. And this works as follows. So the starting point is something realized by Anton Zeitlin a while ago, actually. That is, you can view the vector space of the L-infinity algebra of Yang-Mills theory as a tensor product of, well, the color Lie algebra G, as we reviewed for Schoen-Simons, and some other kind of algebra, which we'll see in a second is a C-infinity algebra. So again, this tensor product notation is just a fancy way of saying that the objects in your theory are G-valued fields. So the fields and the gauge parameters and equations, etc., they live in this Lie algebra frac G. And so in notation I'm using is this one here. So a general object in the space has an expansion XA TA, where TA are the generators of the group. Lie algebra. And now we can relate the L-infinity structure that I just defined to a kinematic kind of algebraic structure as follows. So if you write X as XATA, you can write the differential B1 as an M1 acting on XA. So A is now just a label index. You sort of, it's not Lie algebra value anymore because I've taken out the Lie algebra generators. And for the B2, I have this contraction with the structure constants, and that defines now a new product M2. And similarly for the base B3, where now we use two structure constants, etc., etc. So the claim is that for Young-Mills theory, these M1, M2, M3, they form a C-infinity algebra, which is the homotopy version of a commutative associative differential graded algebra, which is analogous just to the differential forms we had for Schoen-Simons theory. Excuse me. So while for Schoen-Simons theory, the M2 was just associative, so these two terms here were just equal, so this difference would be 0. In the C-infinity algebra, this is corrected. Now with a 3 product, M3, which is what we defined here, and terms similar to what we've seen in L-infinity algebras, except now that the 3-term Jacobi identity is replaced by the 2-term associativity relation of a C-infinity algebra, and that's was exactly analogous to Schoen-Simons theory. Okay, so that's just the basic kinematic algebra that works for any formulation of Young-Mills theory. But now I can explain to you why this formulation with the phi was convenient. Remember, we had this silly-looking auxiliary scalar phi, but in fact that allows you to define in a nice way this extra structure, which I mentioned in the case of Schoen-Simons. So this extra structure is manifested in this form, namely an additional Z2 grading of the underlying vector space, which is thanks to the phi and which allows us to define the B operator, the analog of the B operator. So here I've written again the complex, now the complex of the kinematic algebra. So the objects are still denoted by the same letters, but the Lie algebra dependence is gone. So nothing here carries a Lie algebra index. And I've grouped the gauge parameters and the fields in this particular fashion, because then you can see what the B operator does. So it's again an operator of opposite degree to M1. And the actions basically, if you see my cursor here, it goes from phi to lambda, from E mu to A mu. You see sort of this isomorphic structure here if you go back diagonally back. And this is in fact the action of the B operator. So as an example here, if I act, for instance, on a field, so a field has 2 components, A mu and phi. This just means I pick out the scalar component. So B of this thing is equal to phi. And I view it, I reinterpret it, if you like, as an element of K0. So there's a degree shifting going on. And that's why B has intrinsic degree -1. Again, B squares to 0 because you have sort of this nilpotent structure here. E mu goes to A mu, but then A mu doesn't go any further because only phi gets mapped to lambda, and then of course it stops. So B squares to 0. And more importantly, well, equally importantly, you have the same kind of anti-commutation relation between the 2 differentials, M1 and B. They anti-commute to box, and the way to check this is just to work it out on the fields, and you see why this formulation with the explicit boxes appearing here was very useful, because then this just comes out without having to fix a gauge or do anything like this. So this form will be particularly convenient for us. Any questions so far?
Yeah, I have a question. So this box in the abstraction that you want to make, it's what? Because here you gave examples where this box is very concrete. But yeah, what is the characterizing?
Well, the box.
If you give me any theory.
Here the box is just the box, the D'Alembert or the Laplace operator.
Yeah, I understand. But if you give me any other theory, where should I look to find a box? Like, what is box in the abstraction?
I guess the abstract way of thinking about it is that you're given two differentials, M1 and B, and the box is whatever the anti-commutator gives.
Oh, okay, I see. Okay, so
the
B
M1
is
and B are
fundamental.
the abstract objects.
I see. Okay.
Things. Then you can, whatever the anti-commutator gives you, you call it box.
Okay, thank you.
Okay, so this was the kinematic algebra, and it has this little extra structure. It has the B, thanks to this formulation, which is nice and local and doesn't require gauge fixing. So where's now this extra structure that I mentioned in the case of Schoen-Simons? It's also there, except it's much more complicated because everything only holds up to homotopy. So let's just remind ourselves how this went in the case of forms. So we have an associative algebra. Well, in the case of forms, we had an associative algebra. Here it's associative up to homotopy. So I call it associative type algebra. But it turns out that there's also a hidden Lie type structure. And there's a Lie bracket. Well, not quite Lie bracket, close to a Lie bracket, which is again defined as the failure of B to act via the Leibniz rule on M2. So that means it's this combination of terms. I act with B outside and then I move it inside. So this should be 0 if I had the Leibniz rule, but it's not. So I give it a new name. I call it little b2. And then this object is not 0 and it defines, in fact, an interesting structure. It comes close to be this thing which we called BV algebra before. So just to remember, it means you have a commutative associative product M2. You have a differential that squares to 0, but is actually of second order. So that's a technically precise term. It doesn't act via the Leibniz rule, but it's of second order. And one way to express this is to say that the B2 defined by this formula obeys the Jacobi identity and a compatibility condition with M2 that was analogous to Poisson algebras. So that was just the BV algebra we introduced earlier. So do we have a BV algebra? No, not exactly. The space K, the kinematic vector space, fails to be a BV algebra for several reasons. First of all, M2 is not associative because it was associative up to homotopy. It was a C infinity algebra. Now that you could still fix by putting a little infinity sign at the BV. That's also a notion which I haven't defined, but that is well known to mathematicians, which is a BV infinity algebra. Is it that? No, not quite. Again, because the two differentials, they don't work together well. If they have opposite degrees, if they would anti-commute, everything would be nice, but they don't. They give you this box. And hence, this is called BV infinity box algebra, which is a terrible name if you think about it, but it's not due to us. It was due to this gentleman who proposed it precisely in the context of color kinematics duality, which is called, as it is called, which is the foundation for this double copy business. So here's just one example of a relation that is modified because of the box being here. So if M1 and B would just commute or anti-commute, you could check that the M1 acts as a derivation on B2, for instance. M1 started as an object that acts via the Leibniz rule on M2, but on B2, defined like this, it doesn't work out because I have to commute M1 past the B. And whenever I do this, I get a box, and the box generates in a product terms like this. So box is partial mu, and it distributes like this. So I get these kind of funny anomaly terms. And I get them in all kinds of higher complicated relations. And so this is a very complicated looking algebraic structure. But that's what you get. That's what's present here. And we have to come to terms with it. And so that's what we have to work with. Okay. So actually, I'm using more time than I thought, but so I still have basically like half an hour. Is that correct? Or
yes, exactly.
Yeah. So it will be more than enough time. So first, is there questions on this part. So we have Young-Mills theory, which is an L-infinity algebra. There's a notion of stripping of color, which gives you a C-infinity algebra. And then the C-infinity algebra has this hidden structure due to the B operator, the B ghost. And that is a Lie-type algebra, a BV-type algebraic structure. So it means there's the C-infinity part. There's something that wants to be also a Lie-infinity part, an L-infinity part, but they don't quite work together because of this box failure. So the C-infinity subsector is really a subalgebra. It's a proper C-infinity algebra. But the L-infinity algebra that you would like to have, in the same sense that you have a Lie algebra in BV, is obstructed due to this box business. And the whole object we call BV infinity box. Okay, so that's what you have in Young-Mills theory, and it turns out that that's the structure you need in order to make sense to double copying Young-Mills. So that's now the last part of my talk, the fourth part. Sorry, I'm beginning to lose my voice, so I have to wrap up before it's gone completely. All right, so this is what's called double field theory. And it was called double field theory for completely, well, not completely, but for pretty unrelated reasons. So you see double field theory, and then there's also the double copy in the amplitude context. So any suggestions that could be related sounds, of course, completely stupid, but it turns out that the double in both names is in fact very closely related. And that's what I'm going to explain now. So I want to show in which sense double field theory is the double copy of Young-Mills theory. So recall that Young-Mills theory was the algebra K tensor G, where G is the color Lie algebra. And now the idea, motivated by the amplitude business, is to replace K by a second copy of itself, which we call K bar. So it's exactly the same kind of algebra, except there's a second copy for every function, for every field, and also on the coordinates on which things depend. So now objects in this tensor products are naturally functions of two sets of coordinates, x and x bar. And that's the origin of the name of double field theory, that it depends on double coordinates. Now in this total big space, K tensor K bar, I have two natural differentials of opposite degrees, which play the role of M1 and little b. So there's the big B1, which is just the sum of the two differentials. So I have M1 on K, and I have a M1 bar on K bar, so I can bring them together like this. And I also have two copies of the B. I have a B and a B bar. And it turns out that this object B minus is the useful one. So the difference between the two is a good object. They both square to 0 because M1 and B square to 0. You can check. And there's a version of this anti-commutation relation between M1 and B, which is that big B1 and B minus, they anti-commute to delta, which I call delta here. And delta here is just the difference between the two, the D'Alembert operator on one factor and on the other factor. So it's box minus box bar. So this actually means that on this big space, I have again an algebraic structure of this kind, a BV box, BV infinity box, or BV infinity delta in this case. So there's again a C infinity algebra, that's a proper C infinity algebra, and another subsector that wants to be an L infinity algebra, but that's really obstructed by delta failures in this case. But what we want is a real field theory, and a real field theory needs an L infinity algebra, proper L infinity algebra. And we can solve this by going on to a suitable subspace, which eliminates the delta failure. So here I consider the subspace of K tensor K bar, where all objects are killed by delta, this operator here, and by B minus, the operator here. And it turns out that if you work out the chain complex obtained by the tensor product, which is, you start with a 4-term chain complex, and then it gets longer if you take the tensor product of 2 but then you have to impose the B minus, it shortens it again a little bit. And if you then work out the details, you find it is precisely the complex that defined double field theory. Double field theory was something introduced by Chris Hull and Barton Zwiebach in 2009, coming from closed string field theory. And here, the complex is precisely re-derived from this double copy construction. So just for concreteness, at the level of fields, which lives in this part of the tensor product space, you have these kind of field components, which is E mu nu bar, which is the tensor field, the most interesting one, because it has a symmetric part, which is the graviton. So you naturally get the graviton in this construction. It has an antisymmetric part, which is the B field, and then also a trace part, which is the dilaton. And then there are a bunch of auxiliary pure gauge fields here, which make the formulation actually pretty neat. And this is also exactly what comes out of string field theory. Okay, so that's just the vector space. That's already neat that it comes out correctly. You get exactly the fields of double field theory you would expect. You also get the right gauge symmetries of double field theory, which is a double copy version of linear diffeomorphisms. You get gauge for gauge parameters, in fact, because you introduce higher kind of redundancies, because you create in the tensoring of two spaces, you create a longer chain complex. So all this works out very neatly. But of course, in terms of the general dictionary between L-infinity algebras and field theories, that's just the free theory. So if you go back to the general dictionary, what we have is the differential, so the B1, which defines the quadratic term, or the linear part of the equations of motion. So that's just the free theory. Not too exciting. So what about the nonlinear structure? What about the higher products of the algebraic structure? Or what about the interactions of this field theory, double field theory? So that can be done as well. So the nonlinear structure first requires a higher bracket, like a 2 bracket. So there's a B2, which works, which is just given by this expression here. So we had the little B2, again, defined on the Young-Mills side. So there's this Lie type bracket on the Young-Mills side. And then there's the M2, the associative type product of the C-infinity algebra. If you take this combination, B2 bar with M2 bar, and then minus M2 times B2 bar, this actually obeys the right Leibniz relation with B1. And on that subspace, we consider this is actually equal to B minus on M2 tensor M2 bar. So this does obey the Leibniz rule on the subspace with delta equals 0, because on this subspace, B1 and B minus anti-commute, because delta is 0. So that's all you need to check this. And next, you want to check that B2 obeys Jacobi up to homotopy. In order to check this, you have to define the proper B3 using the inputs of the BV infinity box algebra of Young-Mills theory. Because if you have that, then you have the full gravity theory to quartic order. And this can be given, and it just uses the ingredients that we get on the Young-Mills side. So there's the B2, and then there are higher maps that enter this definition of BV infinity box, which I haven't actually given you. In fact, we don't know it to all orders. We only know it to the order of the quartic theory. But there, everything works out. And using these ingredients, you can also define the B3 and then check that the Jacobi relation up to homotopy holds. So just as an illustration, at the level of cubic couplings, where you need only the B2, you can work out the cubic part of the gravity action, which is written here. And this is, in fact, the simplest version, I think, that anyone has ever seen of the cubic gravity theory. The original double field theory action, the cubic order by Hull and Zwiebach, was already much simpler than what you could normally find in the literature. But this version here is even a much further field simplification, but yet field redefinition equivalent to the form of Hull and Weber. So this double copying somehow brings you land automatically on the in the form of the simplest action. Okay, maybe just for amusement, because I found it super intriguing when we realized this, is how the double field theory gauge transformations, the diffeomorphisms, in fact, emerge rather directly from the cubic vertex of Young-Mills theory. Namely, this works as follows. So if you look at the B2 on the Young-Mills theory side, and you take out the structure constant, so that's the color stripping we have now done several times, and you just give a name to what's left. I called here bullet product between two objects, some sort of kinematic product, or it's part of the M2. And then you write down what it is explicitly. Is this expression here between two vector fields? It looks a little like the Lie bracket between two vector fields, but it's quite a bit different, because you see here a metric is used to construct indices. In fact, there is a metric, of course, in Young-Mills theory. But this combination of terms, what we call here bullet, is exactly what defines the generalized Lie derivative of double field theory, in the sense of this field basis, where the first order part in fields of the gauge transformation looks like this. So there's one term which involves the auxiliary fields F bar and E. But if you look at just precisely the terms that couple lambda, the gauge parameter, to the fields E mu bar, and you take one index to be inert, then this is exactly given by this bullet product that you read of directly from the three vertex of Young-Mills theory. So I found that kind of baffling, that the diffeomorphisms of general relativity in this double field theory form are more or less directly encoded in the three vertex of Young-Mills theory. But anyway, that's just kind of a curiosity. It works for all L infinity brackets of the cubic theory you could want. Okay, so I'm almost done. Let me just say a few words.
Question.
Yes.
So how does your B3, big B3 look like? Do you have an expression for that?
I do have an expression, but unfortunately I have not on any slides here.
Yeah, but what objects does this
yeah, so it's so there's this BV infinity box algebra that has various higher maps that are analogous to the B3, B4, etc. of L infinity algebras, but encoding the homotopies in various other kind of senses. For instance, in the BV algebra, you have this compatibility condition between the two product and the two bracket, some kind of Poisson compatibility. And also that relation does not hold exactly, but up to correction. So that introduces different kind of homotopies. And then there are also those more usual looking homotopies for the little B2 not being Lie anymore. So there's a little B3. Then there's the M3 of the little M3, because you have a C infinity algebra. So there's a whole slew of maps that is already there, hidden, normally not visible in Young-Mills theory. And if you have a complete list of all these maps and the relations they satisfy, then you can build the B3. So we had this in the paper with Felipe, Roberto, who's in the audience, and Christoph, almost exactly a year ago. I can give you the reference, or after the talk, I can also get the paper and show it to you. But it's quite a bit, it's pretty complicated, but it's an honest construction in the sense that it really obeys the L infinity relation, and it really only uses the ingredients that are present in Young-Mills theory proper. So in that sense, it's really an honest construction, but the expression is kind of,
so this construction involves probably like a data, like a specific data coming from in Young-Mills, right? Because
yes.
at this point I can do the same thing for open string field theory as well, like double it in the same way.
Yes.
But like in the quartic order, I will expect a failure to like in getting L infinite algebra, right? Yeah, so like, where is the data from Young-Mills center? Which product that gives you that
Okay.
figure?
Yeah, we can look at the explicit formulas after the talk if you
Right.
want.
Thank you so much.
That's interesting. But as I emphasized, it really uses only the structures that are present in Young-Mills theory proper. So if you could find the same kind of structures in open string field theory, then you can just take over the construction for closed string field theory, I think. So that would be kind of interesting, but we should discuss it afterwards. Okay. So yeah, so this is just one slide on this thing called weakly constrained double field theory. So there's a subtlety in the way you implement this constraint delta equals 0. So I was just saying before, well, we go to that subspace delta equals 0, but delta is a second order differential operator. What exactly do you mean by this? Operationally, the simplest way, which is what I've used so far, is just to say, well, whenever I have box or box bar, I identify them when they act on any fields, gauge parameters, or any objects in the theory, and very importantly, also on their products. And that effectively means that I just identify the coordinates x and x bar. So if the coordinates x are the same as x bar, then of course box is equal to box bar. And I've gone back to the d-dimensional space. So initially, if I have a Young-Mills theory in d dimensions and I have two copies of k and k bar, then I tensor, then I get something in 2D dimensional space. And it turns out that that n equals 0, what's called n equals 0 supergravity, is most efficiently formulated. So sort of this factorized form is double coordinates. But then eventually you have to identify the coordinates, which is strongly constrained DFT. But you only use it in the form of this constraint. So in that sense, it's a reformulation of n equals 0 supergravity. So that's what I did so far. However, we know from string theories that this is not necessary. There should be a weakly constrained DFT, double field theory. We do impose this constraint box equal box bar on fields and gauge parameters and everything, but not on products. Now, the product of two objects satisfying this constraint in general does not satisfy the constraint. So you have to project out whatever fails. And this makes the whole construction extremely non-trivial. But we know from string theory on toroidal backgrounds that this should work, because that's how Kaluza-Klein and winding modes are encoded in this theory. And in principle, you could just derive it from closed string field theory via something called homotopy transfer. But in practice, you can't. It's just too complicated. So we were wondering, can we use this double copy framework of achieving the same goal? The concrete goal here is to push this weakly constrained double field theory to quartic order. So in the original paper by Hall and Zwiebach, this was worked out to cubic order, where this consistency problem kind of trivializes. But then once you go to quartic order, it becomes very non-trivial and has not been possible to explicitly construct this vertex so far. But here we found a way, at least if all dimensions are toroidal and doubles. And the strategy is the following. So you first go to this total space K tensor K bar, and you view the elements as unconstrained functions of doubled coordinates, x and x bar. And as I mentioned before, this by itself is a rich algebraic structure. It's a BV infinity delta algebra, delta being box minus box bar. So it's an interesting algebra, but it doesn't have an L infinity, a proper L infinity algebra as a subsector. So to get the proper L infinity algebra, we then do homotopy transfer to delta equals 0. That's still not a proper L infinity algebra, because you start with something that is not of the standard type. But you can fix this by performing an extra non-local shift of the B3. So we have an explicit B3 that makes the generalized Jacobi identity work for weakly constrained theory. So in that sense, we have now the genuine L infinity algebra of weakly constrained fields, and hence a weakly constrained double field theory. The concrete construction is very technical, and the final result is super complicated, but it's just a proof of principle that this framework is very rich and powerful, because it allowed us to do something here which I've tried for more than 10 years and could never achieve, but here you can do it. So that's, I think, a sign that this is very powerful. Okay, so I'm basically done. Let me just summarize and end with an outlook. So I've given an off-shell local engagement variant double copy construction to quartic order in fields. And the strategy here was to view Young-Mills theory as a homotopy Lie algebra or L-infinity algebra, as this tensor product K tensor G with the kinematic C-infinity algebra K and the color Lie algebra G. And then to realize that K is not just the C-infinity algebra, but has a hidden Lie-type structure as well, which makes it into a BV-type algebra, but BV up to various modifications. But this is good enough, at least to the order in which we can do it so far, to actually construct the L-infinity algebra of double field theory by taking the tensor product K with a second copy of itself. I should also mention that this works as well, and is much simpler for self-dual subsector of Young-Mills theory. So for some of you may know what that means. This was worked out by Roberto, Felipe, and Silvia Nagy a few months ago. So a very nice paper. And so what are the open questions? The biggest one, of course, is that we're supposed to do this to all orders, even just for strongly constrained double field theory. We've done this to quartic order, and there the construction is already quite complicated, especially the structure of the B3 that I haven't given you is quite complicated. So in order to have a complete first principle proof or derivation of double copy, we really have to do this to all orders, which requires understanding this underlying BV infinity box structure much better. In particular, of course, we require an all-order characterization, what this algebra really is. We can't really give yet an all-order characterization of these higher Jacobi and Poisson type identities in the way we know how to do it for A infinity and L infinity. So this is still an open research problem, even just to state what are the general relations that this kind of algebra should obey or define. And then the second step would be to actually prove that Young-Mills theory has this algebra in it to all orders, not just to quartic order. And then third, finally, to then do the explicit double copy construction to all orders. And if one had this would be a complete first principle proof of double copy. It's an ongoing program, but I'm confident that we'll get there. And then there are all kinds of possibilities. So we could imagine finding explicit map between the classical solutions on both sides, the classical solution of Young-Mills and of gravity or double field theory, and dream of applying it to black holes and gravitational waves problem, who knows. And in the weakly constraint setting, you can even revisit the quantum UV properties of gravity, because now it's not just general relativity in some funny formulation, but it has genuine massive string modes in it. So they run in loops, so everything can change. And in fact, in the original argument by Sen, why this theory should exist, it was pointed out that if you really were to derive this from the full closed string field theory by just integrating out everything that you don't like, this theory would inherit the UV finiteness of string theory. Now, this is not what we're doing here. We're getting directly from a double copy, so everything is different, but it's still interesting to revisit it. Okay, thank you very much. Let me stop here and we have time for questions, I guess.
Thanks a lot, Olaf, for the talk. So, and thanks for inaugurating the 2023-24 session. Do we have any questions for Olaf?
This little b, it's given. I really don't understand where it comes from. I understand M2, M3, but b, you need to find it in a theory. How it because if I understand correctly, B is the fundamental guy, not box, right? Box is a consequence of B.
Yes, yes, right. Yes, for instance here. Well, as I said, in string field theory, there's a B ghost. In Young-Mills theory, there's this B operator, which we wrote here. In different formulations of Young-Mills theory, you can also find the B, which looks quite different. So for instance, this paper by Reiterer, which I cited a few times, he uses a very different formulation of Young-Mills theory, which has some advantages and other disadvantages. It's not so useful for double copy, but he can establish an algebra, a special case of this BV infinity box for a strict I think it's strict. Maybe some of the audience can correct me if it's wrong, but it's a simpler version in pure Young-Mills theory. But the B is actually a differential operator, so it would be awkward to implement it as a constraint on the double copied gravity side. So you can just, one way to answer your question as well is like, here's a long list of theories, Chern-Simons, Young-Mills in one formulation, Young-Mills in another, and all these theories have a B operator or B ghost. Also string field theory, of course. But there's a slightly more conceptual reason, which I briefly mentioned, is that the B is the object that you need to impose a gauge fixing condition. And then once you have imposed the gauge fixing condition, it's what you need to invert the kinetic operator to get the propagator. So then it's something B over the B times the inverse of the kinetic operator after gauge fixing, and the gauge fixing is something B psi equal to 0. So it's knowing that there's a B is kind of like knowing that in principle you can gauge fix. And the concrete ways of doing it can vary a lot depending on how you want to do it. But knowing that there's a B or the choice of B is analogous to the choice of a gauge fixing condition. I don't know if that helps.
Okay, thank you. But this B in string theory comes from the first quantization of the worldsheet, right?
Yes.
Then in this gauge theories you're talking about, can I understand this B as coming from first quantization of word lines?
Yes. So that's what Roberto was referring to. You can indeed do that. Yes. So you can define word line theory, quantize it, and there's a B and a Q, which is the M1, and interpret it in that way. I don't know if Roberto wants to add anything to that point. He's still around.
Yeah, so, yeah, no, indeed, as Olaf said, essentially the way we derive this form of Young-Mills, meaning namely with the phi, comes exactly from the BRST quantization of a word line theory with n equal to supersymmetry. So B, in that sense, is the first quantized B ghost.
Oh, I see. And in this double copy story, can you do the same or no? Like, can you translate everything we're doing at the second quantizer level to the first quantizer level? How it goes?
Well, it would correspond, I mean, the pure n equals 0 supergravity, so in particular with no doubling of coordinates, would correspond to still a spinning particle with n equal 4 supersymmetry on the word line. And in that case, it would also have a B operator, but that B operator would correspond to the B plus. So instead, we doubled everything, and then meaning even like what in string theory would be the center of mass, the position. And hence you have the B bar, and you can have B plus, B minus.
Oh, okay, thank you. Okay, thank you.
So do we have any question? Okay, so if not for now, I will stop the recording and we can see if people have more questions after. Okay, so